Hello, what you're seeing now, the thumbnail of this video, is a few collections of news headlines from recent years, including one from today at the time of recording this. It's quite a familiar sight for those who read the news: war and militarism. And an immense amount of money is poured into war and military. As it relates to Canada, more recent news, we've committed in excess of $60 billion to our own military defense. Another 30 billion some dollars to aid other countries at war. So military defense is very much an ongoing consideration in our country. And military superiority has always been about technological superiority. As foreign powers increase their military spending, as a nation, it's an unfortunate truth that we must also pursue such technology to protect ourselves. So we come to a critical aspect of military defense, which is stealth, perhaps a more pacifist technological pursuit than weaponry. That is, the ability to avoid enemy detection. As it relates to aircrafts, there's a number of methods to improve stealth, one of which is radio wave detection. Some advanced materials are capable of absorbing these waves, but it requires quite complex architecture. Now, radar is a fundamental part of aircraft communication technology. Essentially, commercial airplane will receive and send back radio waves to a transmitter to communicate its location, which is a great benefit for passenger planes, but certainly not for stealth. The radio signature of an aircraft indicates its visibility to radio, and it's measured by something called a radio cross section, RCS. Essentially, how many incoming waves are reflected off the object. So it's represented in this circular diagram here as a function of incidence angle. It's defined numerically as a surface area, so the size of the sphere that would generate the same wave reflection in the same field. A traditional commercial plane has an RCS like this one, considerable magnitude in every direction, whereas a stealth plane like this comparison piece here has reduced the signal with just large peaks where there are prominent geometrical protrusions. If you look at the geometry of different stealth planes currently in use, it becomes clear that this is very much still an open issue. Um, the ideal shape would be an infinite plane. There'd be no reflection, but planes have engines, internal components, and so on. Um, the abundance and location of detectors, orientational considerations. So the development of a model that can assess the effectiveness of different geometries at reducing the radar signature of a plane is therefore a very fruitful investment for a nation that is committed to spending many more billions of dollars on its military in the future. What we've done is used COMSOL to build a radar model from scratch, so both in 2D and in 3D. We can simulate incoming waves at a desired frequency and incidence angle with the electromagnetic wave equation. So it's a vector wave that comes from Maxwell's equations. The background electric fields comprised of plane waves. In 2D, they're polarized in the z direction, and they propagate in the xy plane as a function of phi. In 3D, it's a full vectorial field, so the waves propagate in all directions. The total field's decomposed into two fields, background and scattered field. It's a portion of the wave generated by interaction with the object. And we can compute the RCS using these equations. So in 2D, this yields like a relative per unit length, and in 3D, it's a full area. These values are computed from the far field scattered electric field, which can be transformed from the near field with this integral relation here. So the model in 2D, the near field relative to the source radar and the far field, similarly in 3D with this outer shell being the near field. There's an impedance boundary condition here where it removes the need to solve for the geometry inside the plane. The plane isn't a perfect conductor, but it does absorb some amount of energy, so it is a decent working assumption. Now, the first method we employed was a topological optimization, where we defined a rectangular region and gave the model complete control over the geometry with a fixed total area. So that yielded this pill-shaped body. Adding a weight function, which slightly prioritizes reflection from the front aspect of the plane, yielded this fish-shaped geometry. This weight function is justified because the cockpit usually contains more electronic components, and that's at the front of the plane. Also, it is the first point of detection for a body entering a radar field. So we extracted the shape and converted it into a geometric part and ran it through the model, and it gave these results for the relative electric field. So essentially what a distant observer might see. Compared to a benchmark airplane, the scattering is much more concentrated towards the back here. And the total variation in the electric field is a lot less compared to the benchmark. So it is much improved. This is reflected in the RCS diagrams where you see a large region of invisibility at the phi equals 0 incident angle, and these very large spikes in visibility at the perpendicular angles. Compared to the benchmark plane, which is really all over the place. It does share this nice invisible region at the front because of the similarities in the nose geometry. However, when you look at the overall visibility, you notice that it's largely unimproved. It can be interpreted geometrically as the integral of this graph, and they're quite similar. We can import the 2D part into the 3D model and run the simulation. This is the far field scattering pattern, so essentially where the energy is going after hitting the plane. There's no true noticeable improvement here, but in the relative electric field, there's a notable decrease in scattering from the incident angle, and overall more regions of low scattering. That's especially visible in this cross-sectional view here. So compared to the benchmark on the right, you see many more regions of less variation in the electric field, and indeed a decrease in the magnitude as well.
The second method we used is parametric optimization. In this method, we gave COMSOL basic shapes and let COMSOL control the side length and angles to optimize our CS signature. In these next three examples, you can see the various shapes that we used and the various optimizations that resulted from it. Looking at the final product here and comparing it to a control plane, we can see that each shape has different decibel scales showing different amounts of RCS reflection, but each shape also has a unique RCS signature. When comparing these, we can see the pros and cons of each model, which we will use to construct a 3D plane later. We took one of these models and we extruded it to 3D. It yielded results such as these. In this far field norm compared to our control plane, you can see not much difference, showing very similar outer field results. Now looking at it from a top-down view, it also looks very similar. However, when looking at it from a side-on view, we can see much more blue, showing much less scattering in these areas. Now moving on to method 3, as I just mentioned, we used each of the pros and cons to construct a plane in OpenVSP, which is a software designed by NASA to make planes from scratch. This allowed us to make a plane with slightly more detail. As you can see here, the meshing is a little bit more complicated. However, when we move on here, we can see, again, a very similar plane to the control one in terms of field normal vectors. Moving on to the top-down view, you can start to see some of the benefits. As you can see, the plane that we designed in OpenVSP shows a lot more or a lot less scattering from this top-down view. Now moving on to the side-on view, you can also see way less scattering, showing that radar hitting the plane from the bottom and the top is going to have much less success in identifying the type and the location of aircrafts flying above. Finally, it's important to note various issues and future improvements with our geometry. Currently, our mesh is coarse. This means that results are not that accurate, and as noted in a lot of the far-field graphs, they're often very splotchy or have blots on it. By using a finer mesh, we'd be able to smooth out these blots and get a more accurate reading. Currently, the focus is also very heavy towards the 2D computation, which is obviously not how planes are constructed in real life. Computational power restricts this, as if we had access to more computation power, we could optimize parameters in 3D, making a more complex and a more complete geometry. Because of the current 2D geometry layout, a lot of our aircrafts look identical from the side. As I mentioned, if we can use it in 3D, more details will be able to be expressed on the side, leading to better simulation results. For goals for future improvements, we would like to allow for global optimization over any relevant angle, which would allow us to identify better scattering trends and any potential secondary sources of scattering. Both of these are very important, as secondary sources can give away an aircraft just as much as a primary source can. As far as optimizing parameters go, we would like to be able to automate surface fine-tuning, and allow for emphasis on specific directions in the plane. We also want to give opportunity to all pick different materials and compare them to one another in order to reduce costs and reduce energy consumption, as current outer materials of stealth aircrafts end up creating a lot of energy, which needs to be dissipated somehow, which can be picked up by infrared signaling. Thank you for listening, and we hope that you guys choose to invest with us.